In this video, we're going to talk about how to find those oblique asymptotes. And we can see from the function given here, well, one, we could calculate our vertical asymptote, and we can recognize it on our graph at x is equal to 1. And we can see how the graph is approaching that as it goes up and down. And we can also see an oblique asymptote, but it might be useful to be able to calculate exactly what that oblique asymptote is. So one way to think through an oblique asymptote is to take our rational function and to think about it in a different form and to try and write it in more of a polynomial form. We can do that by a process of long division. Again, we're just going to think about trying to get it into a different form and see what that tells us about this type of function. This is a brief reminder of how to work through a long division. I want to see how many times 2x will go into x squared, and that's going to be 1/2 x times. Then I will multiply 1/2 x times 2x is x squared. 1/2 x times -2 is minus x. Just like normal long division, I want to subtract. I get 0x squared, but I get 4x, and then I'll bring down my -2. 2x goes into 4x 2 times, so we get +2. And 2 times 2x is 4x, 2 times -2 is -4. We want to subtract, giving us a remainder of 2. And the value of this is it allows me to take my function f of x and rewrite it as 1/2 x squared plus 2 plus 2 divided by 2x minus 2, or let's just go ahead and change that to 1/x minus 1. And then we'll remind ourselves about how horizontal asymptotes work. Horizontal asymptotes are based upon the limit of the function as x approaches infinity. So let's ask ourselves that here. As x is approaching infinity, what is happening to this function 1/2 x squared plus 2 plus 1/x minus 1? Well, your first response may be, well, the limit doesn't exist. This leading term of 1/2 x squared means that the graph is going to shoot up towards infinity. It's never going to stop getting bigger and bigger and bigger. But I'm more interested in this final term here. What is the limit of this fraction as x approaches infinity? And we'll see as x gets bigger and bigger and bigger, the denominator does as well. So this fraction right here approaches 0. What that allows us to conclude is if we take the limit as x approaches infinity of the function 1/2, oh, I had an x squared on here. It shouldn't have been x squared. It should have just been x. My apologies. The limit of 1/2 x plus 2 plus 1/x minus 1. Well, because that final term, 1/x minus 1, approaches 0 as x goes to infinity, this is the same thing as the limit as x approaches infinity of 1/2 x plus 2 without that fractional part at the end. What this tells us is as x gets bigger and bigger and bigger, as x gets bigger, f of x is going to behave like the linear function 1/2 x plus 2. And so if we come back up to our graph and we graph that line 1/2 x plus 2, what we're going to notice is it fits in precisely visually where we might expect that oblique asymptote to be. And in fact, this is our oblique asymptote. And again, the conclusion we're drawing is as x gets bigger and bigger and bigger, our curve is going to get closer and closer and closer to that line because the limit as we go to infinity is going to be the same for those two functions. They are going to increasingly behave like the linear function. So that's our process for finding oblique asymptotes. We can use long division. And the function that we get when we do our long division is going to tell us what that oblique asymptote is. So here's another function. If you want to pause and try to do the long division you can, and come back and see if you got it right. One mistake we might make when trying to do this particular long division would be to not put all of our terms in the correct order and to not include them all. Notice in the numerator there is no x term, but we still need it to be represented in our long division. So I'm going to put a plus 0x there. And we check how many times does x go into negative x squared. Well, that's going to be negative x. We get negative x squared plus 4x, and we want to subtract. So we'll have negative 4x plus 1, and then we will get negative 4. So negative 4x plus 16. Again, we are subtracting. Get negative 15 as our remainder. So we get minus 15 over x minus 4. But again, the part that we care about is this linear function here in front that represents our oblique asymptote. Now, do keep in mind that the only way for us to get a linear quotient is if there is a particular relationship between the numerator and the denominator. And that is if the numerator has a degree that is exactly 1 greater than the degree of the denominator. That's the only way to get a linear oblique asymptote. You can imagine if the difference in the degrees was bigger, our result from dividing would have a higher degree. That's going to be a way to maybe start thinking about those nonlinear asymptotes, but we're not too concerned with those here. So we have an asymptote that is oblique at negative x minus 4. We do want to also check to see our vertical asymptote, and we do have a vertical asymptote at x is equal to 4. And so those are the two asymptotes for this particular graph.